So these are the solutions to assignment 7. In question number 1, we are given that the logical effort of a NOT 7 gate is X and the logical effort of a NOT 2 gate is Y. What is X divided by Y? So a NOT 7 gate is one which has a 7 stack of PMOS. So there are 7 PMOSs here connected to VDD, and there are 7 NMOSs here connected to ground. So that's A1, A2 till A7. Similarly, A1 to A7. Now, this is Y, the output of the NOT 2. And in a NOT 2, it's just the same circuit except with 2 PMOSs instead of 7 and 2 YMOSs. Right? And we have A1, A2, A1, A2 and Y. This Y is equal to A1 plus A2 the whole bar. This Y is equal to summation I equal to 1 to 7 AI the whole bar. Now, since this is a 7 stack, this has to be 7x the size of the reference PMOS. Reference PMOS size is 2, so this will be 14. Of course, these are all just 1 stacks on the NMOS, so we will just have the reference size of 1. Since it's a 2 stack here, it is 2 times the reference size. Reference size is 2, so this is 4. 2 into 2 is 4, and we have 1 over here. So the logical effort of any input would be the gate capacitance divided by the reference inverter or the inverter, comparable inverters gate capacitance. The gate capacitance here would be 14 plus 1 on, let's say, the A1 divided by the reference capacitance is 3. This is G07. Similarly, over here, the gate capacitance is 4 plus 1 divided by 3. That's G02. We have said that G7 is equal to X and G2 is equal to Y. And we are asked what is X divided by Y. This is equal to 15 by 3 by 5 by 3. This is 15 by 5 is equal to 3, which is the answer. In question number 2, which of the following statements are false? If the logical effort of a gate A is less than the logical effort of gate B, then the delay of logic gate A is less than the delay of logic gate B. Now, essentially, you can find the definition of the delay in the common definitions. The delay of a gate is simply GH plus P, where G, H and P are the logical, electrical and parasitic efforts of the gate. Now, let's say GA is less than GB. That is what this says. Of course, DA is equal to GAHA plus PA, and DB is GBHB plus PB. Now, it's not necessary that just because GA is less than GB, that even GAHA is less than GBHB. It could be that the logic gate B, for example, let's say the logic gate A is an inverter and the logic gate B is an AND 2 gate. This has logical effort. Let's say this is logic gate A, this has logical effort 1, and this has logical effort 4/3, right? But it could be that the load capacitance here CA, let's say, and the load capacitance here CB could be such that the electrical effort HA is far greater than the, for example, let's say the electrical effort HA is equal to 2. That is CA is equal to HA into the input gate capacitance would be 3, HA into 3, right? So let's say CA is 6, for example, over here, and we'll say that HB is equal to 0.5, let's say, right? You can accordingly get the input gate capacitance here, which would be 4, and so therefore CB would have to be HB into 4, which is 2. So the load here is far more greater than the load here. So because of that, HB is far less than HA, even though GA is only slightly greater, it was only slightly less than GB, right? So it's not necessary that just because GA is less than GB, that DA will be less than DB, or DA is less than GB. This is not at all necessary. So the statement is false. Without knowing what loads the gates are driving, you cannot really say if the delay is lesser. Doubling the widths of all transistors in a logic gate makes the delay half, makes the D of that gate half. Again, doubling, if you make the width as 2 times, it means that the gate cap becomes 2 times. So therefore H logical effort is C gate by C load becomes by half. But just because H becomes H by 2, and of course G doesn't change with width, P also doesn't change with width, right? So therefore D actually does not become, it's not necessary that D becomes D by 2, because G and P are unchanged. So it's going to be H by 2 G plus P is the new value of D, right? And always P is not equal to 0 for any gate. You could have H equal to 0 for a gate, but never P 0. So therefore, it's not that D suddenly became D by 2. Not the case. It's not necessary, is what I'm trying to say. So this is also false, right? Then if the load capacitance of a gate is 0, then the D for that gate is 0. Again, if the load capacitance is 0, then H will become 0, because that's C load by C gate. So GH is equal to 0. But P is never 0. There will always be parasitic capacitance, which is the output the drain to drain capacitance of the gates connected to the output. So this is also false. So since P is not equal to 0, D will not be equal to 0. So therefore this is false. And finally, a NAND 2 gate driving a load capacitance CL always has lesser delay than a NOR 2 gate driving the same load capacitance. Now, reading this, you might be inclined to think that both of them are driving the same CL, and the NOR 2 gate and NAND 2 gate will therefore have the same H, because if you look at it, NOR 2 gate has input capacitance of, it will be 4 and 1 on the PMOS and NMOS, like we discussed in the first problem. So that will be 5 is C gate, so it will become CL by 5. That's the H, right? And similarly for a NAND 2 gate, right? It also has actually 2 and 2 on the PMOS and the NMOS, right? This is what the NAND 2 gate has, so it will become CL by 4, right? So actually H of NOR 2 is less than H of NAND 2. So, but it could be that CL is 0, but again, the question statement says always, so we'll have to assume the most general case, right? So even in the most general case, H of NOR 2 is less than H of NAND 2 if they are both driving the same CL as the question states. And so therefore, but the question is, this is assuming both of them are the same size. Now it could be that if they're both 1x 1x, then this is the respective H's. But it could be that one of the NOR 2s is really upsized to make its H really less. Right? This 4 could become 4 times, like 16 or something, if I sized it up by a factor of 4. To I could have brought down this NAND 2 artificially by sizing up the NOR 2 gate. So you really can't say, because there's no comment made about the sizes. It just says a NAND 2 gate and a NOR 2 gate, right? So given that the sizes can be different, the H's are different, and of course the G's are different, and so you can't say which is greater, which is lesser, because the sizes, there's no statement made about the sizes. So yeah, all 4 statements are false. In question number 3, let a CMOS logic gate sized for equal rise and fall delay implement the following expression. Which input pin has the least logical effort? Right? So let's look at the diagram, right? Let's draw the diagram of this gate. So it's easier rather to draw the NMOS side, A, B, C in series, right? Let's say B, C, and D in parallel. And of course, you can look it up. This is not a self-dual function, so you would have to draw it like on the PMOS side, the dual, you'll have to draw the dual circuit. So this is A, B, C in parallel in series with D. Right? So these all have sizes of 3, 3, 3, and this has a size of 1. And all these, of course, are 2 stacks, so they all have a size of 4. Right? So the logical effort GD, the logical effort of, let's say, GA equal to GB equal to GC is simply the gate capacitance C gate, which is let's say if you take C for an example, 3 plus 4, that's 7, divided by the reference, which in this case is 3, right? And GD is equal to 4 plus 1, which is 5 by 3. So clearly GD is the least, so the input D has the least logical effort. In question number 4, we are asked to find the logical effort of a NAND 4 gate. So yeah, let's draw a NAND 4 gate. So the end stack looks like that. It's a 4 stack, so it's 4 times the reference size. Reference size is 1, so it's 4. And then this is the P stack. Right? It's all 1 stack, so it's just the reference size of 2. Fairly straightforward. Take any input pin, and simply find its gate cap. That's 4 plus 2, 6, divided by, in this case, the reference is, because it's equal rise and voltage, the reference is 3 to 1 inverter, and you get the answer as 2. Similarly, for a NOR 4 gate, we have on the PMOS side, we have a 4 stack, right? We have a 4 stack on the PMOS, and NMOSes, 4 NMOSes. These are all 1 stack, so they have a size of 1, and this is a 4 stack, so the size is 4 times the reference size, which is, reference size is 2, so 4 into 2 is 8. So now the gate cap, let's say these two are the same, is 8 plus 1, 9 by 3, which is 3, right? And then the parasitic effort for a NAND 4 gate, we have, referring to this diagram, parasitic effort, find the total output cap. So it's 2 plus 2 plus 2 plus 2, so that's 4 into 2 plus 4 by the reference parasitic output cap, which is the 2-1 inverter, which has the output cap of 3. So that's 4 into 3 by 3, which is 4, right? And for a NOR 4 gate, that's 8 plus 4 ones, 4 into 1, divided by the reference cap, which is 3. So this is 4 into 2, so this is 4 into 3 by 3, that's 4, right? So the 8th question, the delay of an NOR 4 gate is equal to that of a NAND 4 gate. So we've already seen that parasitic efforts are the same. It's only that the logical effort of NAND 4 is less than logical effort of NOR 4. So the question is, D of NOR 4 is equal to D of NAND 4 only if the NOR 4 has greater size than NAND 4, which is to say that the electrical effort is, which is not necessarily to say that the electrical, which is not the only thing that can make the electrical effort lesser, but yeah, it's one thing that does. So if the question had said if and not only if, then it would have been true, but it says only if, which say that this thing is necessary for the delays to be equal, and that's not true. It could be again that the H of NOR 4 is less than the H of NAND 4 because the NAND 4 is driving a larger load cap. It could be. Question doesn't stop that. So had the question said if, then it would have been true, but since it says only if, it's false, right? This is not the only thing that makes H of NOR 4 less than H of NAND 4. In question 9, we are asked to take a NOR 3 gate. So this is a NOR 3 gate, right? PMOSes have 3 times the reference size because it's a 3 star, and MOSes have size 1, right? 1, 1, 1, and we need to tie all the inputs together, right? We have tied all the inputs together. Now we are asked to find what the logical effort for rise of this inverter is. Now, as you can see in the rise case, it is no different from the regular NOR 3. The resistance is still, R by 3 into 3, which is R. So the reference inverter is still 2-1 inverter. So therefore, we just add all the capacitances, which is 6 into 3, that's 6, 6, 6, plus 1 into 3, plus 1 into 3, right? So now we get that divided by 3, which is simply equal to 7. This is the logical effort for rise, right? Why is this 3? Because the rising case has the same resistance R. or in or it it still has the same pull up current as the 2-1 inverter. 2-1 inverter has gate capacitance of 3, so that's why we had to take 3. Similarly, for fall logical effort 9-3 inputs tied together, right? So we take a 9-3, which is 1, 2, 3, all size 2, 2, 2, and 1, 2, 3, 1, 2, 3, and tie all the inputs together, right? So it's A, this is Y, it's an inverter. This has size 3, 3 times the reference size, which is a 3 star. And the total capacitance on the input would be 2 plus 2 plus 2, that's 2 into 3 plus 3 plus 3 plus 3, which is 3 into 3. And since in the falling case, it still has a resistance of R, right? We were asked what the logical effort for fall is. So GF would be equal to this divided by 3, because the reference is still the 2-1 inverter for this. So which is equal to 5. In question 11, NAND 3 gate has inputs A, B and C, right? Input A drives the NMOS connected to output. This is a NAND 3 gate, NMOS connected to output Y. Input B drives the NMOS above the NMOS connected to input C, which must mean that input C is the bottom of the stack, right? Right? So you need to tie one input to VDD to convert this to a NAND 2 gate. Which input should you tie to VDD? So the idea is VDD comes and then just settles, right? It doesn't ever change. So if you were to tie the input C to VDD, then this node would get completely discharged and stay completely discharged to at 0 volt. So essentially what you would get is this node becomes 0 volt or grounded. So therefore it's actively being pulled to ground. Sorry, this node is actively pulled to ground. So therefore this cap is discharged. So now what you will get is that there is one bit of parasitic capacitance that is never really going to charge up. So therefore it's only this cap and this cap that needs to discharge if you want to pull the output to low. And this is why the earliest arriving signal, which is VDD, stays farthest from the output. The latest arriving signal is closest to output, right? Because all the other signals would have already arrived and all the parasitic nodes would have settled to their steady state values, and so therefore it's only this last guy that would switch, and therefore it would only have a pull down of discharging the output Y cap, right? And so the answer is C. Right? The answer is C. In question 12, calculate the optimum stage effort for the circuit shown below. All the gates are sized for equal rise and fall delay. The input inverter presents a capacitance of 11 lambda, and this is the output capacitance of the this is the output capacitance equivalent of transistor. So directly this allows us to calculate the H of the path, which is C load by C gate, which would be this is 11 power 4. So 11 power 4 divided by 4 divided by C gate, which is 11 lambda. Lambda cancel. So this would be 11 power 3 by 4. So this G is 1. This G is 4 by 3. And for a NOR 4 gate, we would have that we have a PMOS stack that is size 4 so it's 4 times 2, that's 8. 2 is the reference size, and it's a NMOS of stack size 1, so 8 plus 1 is 9, and we get 9 by 3 is the logical effort, which is 3, right? So G is equal to 3. So the total G is the product of all these three things, which is 4. So therefore GH is equal to 11 power 3, and since there are 1, 2, 3 guys, F, which is the optimum stage effort, is GH power 1 by 3, which is 11 power 3 power 1 by 3, which is 11. In question 13, calculate the pull-up logical effort for a low skew inverter where the size of the non-critical transistor is scaled by a factor of 1 by 4. So this is a low skew inverter. So let's first, just draw the regular 2-1 inverter. Right, so that's 2 and 1, VDD ground, A1. It's a low skew inverter, which means the non-critical transistor is this guy, non-critical transistor. And this is scaled by a factor of 1 by 4 when compared to the standard equals rise and fall derivative, which is a 2-1 inverter. So we are now asked what the logical effort for the pull-up is for this guy. So this guy will have to now be compared with an equivalent pull-up current device. So the PMOS would have to be the same size, 2 into 1 by 4, and the NMOS for equal rise and fall delay would have to be half of that, which is 1 by 4. So that is the comparison inverter. So the input gate cap here, G2, is equal to 2 into 1 by 4 plus 1 by 4, which is 3 by 4, and the input gate cap, let's say call it G, or the input gate cap, so let's call this C2, and the input gate cap here, so let's call it C1, is 2 into 1 by 4 plus 1, which is 4 by 4, which is 6 by 4. So G1 will be equal to C1 by C2, which is 6 by 4 by 3 by 4, 3 by 4, which is 2. And those were the solutions to assignment 7.